All right, you guys, lesson 3-2 is all about transformations of parent functions, and we're going to specifically apply transformations to absolute value functions. So I've already pre-made some of our notes here. I just want you to take some time to copy down the unit, the title, and the objective. Sorry, it got a little messy, but our unit is still parent functions and transformations. Please put today's date. This lesson is transformations, Vertex form of absolute value functions. Our objective is to graph absolute value functions in Vertex form. So, transformations. A transformation just changes the position or size of a figure. Transformations can be applied to parent functions. We're going to be seeing things, comparing them to parent functions, seeing these different transformations of the absolute value function specifically today. So if we recall, this right here is the parent function of the absolute value function, and we did put this in our notes yesterday. The most simplest form of an absolute value function is f of x equals the absolute value of x. So it's that operation, absolute value, applied to x. And when we graph it, we get this, okay? So just looking at some key features here, our vertex is right here, 0, 0. Okay, be sure you're pausing the video to get this stuff written down. So our vertex is here at 0, 0. And then looking at our slope, our rise over run, it's up 1 over 1. Up 1 over 1, positive on the right. And then on the left, it's up 1, left 1. Up 1, left 1. Negative on the left. Okay? What we're going to be doing is we're going to be taking a look at comparing this parent function to all of these other transformations of the parent function here on the right. And so what I've done is I have opened up Desmos. So if you're watching this on a computer and you have the ability to utilize Desmos maybe on a different device, you can follow along, or you can just kind of watch and see and look and compare. So the first thing we're going to do is we're going to take a look at comparing the parent function to this first one, the f of x equals the absolute value of x plus 2. So I'm going to go over here to Desmos, and I already have typed in the parent function, the absolute value of x, okay? And so this looks just like the graph on our notes. Now I'm going to type in the absolute value of x plus 2. And we're going to take a look at comparing these. So this red one is our parent function. Now let's take a look at the blue one. What transformation was applied? Well, if we take a look, our function was shifted to the left 2 units. And now look at our vertex is now at negative 2, 0 instead of at 0, 0. So going back to our notes, describing this, we're going to say shifted left 2. Interesting. All right. So that was a left. So that was a translation or a shift to the left. Now let's compare our parent function to this next one, the absolute value of x minus 2. So going back to Desmos, I'm just going to edit this to be a minus. So now minus. And now take a look. Look at this. This was plus. This is minus. So now comparing our functions here. Oops. Okay, comparing our functions here. Look at our parent function, which is red, and compare it to this function, which is blue, the absolute value of x minus 2. This time it was a translation or a shift to the right 2. Okay, so we'll call this shift right 2. Okay. Now we're going to compare the next one. So I'm going to flip back to Desmos, and I'm going to type in the absolute value of x plus 2. Okay, now what do you see happening? What is the transformation? Well, shifted up 2 units. All right, so going back to our notes, this was a shift up 2. And you can see that change in our vertex as well. Our y value of our vertex is now 0, 2, so our y value is 2.
Okay, well, what happens? What do you think is going to happen if I have a minus 2? Okay, so taking a look, red is our parent function, blue is the shift. What was the shift? It's down 2. So we're going to say shift down 2. Now we're going to compare if we have a 2 out in front of our absolute value. So back to Desmos. And I'm just going to edit this and put a 2 out in front. Interesting. Notice that our vertex is in the same spot. However, let's compare the slopes of this line coming to the right and the line coming out of the vertex to the left. Notice our slope is a little bit more narrow. So instead of going up 1 over 1, now it's going up 2 over 1. And so we're going to call that a vertical stretch. Try to picture it if I grabbed both ends of this function and I stretched it up. We're going to call that a vertical stretch. And then we're going to be more specific with this, and we're going to say by 2 or by a factor of 2 because it's being multiplied. So vertical stretch by 2. Now we're going to take a look at what happens if there is a 1/2 out in front. Okay, so comparing this to the parent function, our vertex doesn't change. However, the slopes of each of these sides of the absolute value function, my V shape, the slopes are a little less narrow. And so this is going to be called compress. Think of it if I put a weight on top of the graph and it's going to push those sides down. So this would be compress. Vertical, compress by 1/2. And then the last one, if there is a negative out in front of the absolute value. So going back to Desmos here, let's change this guy to a negative. Woo! Let's zoom out here so you can see that a little better. Take a look. So our red is the parent function. And what's the difference? Well, it's been flipped over. So if you remember transformations from geometry, what is the proper term for a flip? The reflection, specifically a reflection across the x-axis. So reflect across the x-axis. All right, so what we did here is we just discovered some transformations that we can apply not only to the absolute value function, but we can actually apply this to all parent functions and transformations. So over here, I would like you to write a little transformations guide, and we're going to write down some formulas. So transformations guide. Okay. Let's say I have a function f of x plus h. All that means is inside my operator, so inside, for example, this absolute value, we have something being added. So this would be my f of x plus h right here. And what did we see that occurred when we added something to our x value inside the absolute value bars? Well, it was a shift to the left. And so when we see that, when something is being added inside of those absolute value bars, and later on we're going to see it as different types of operations, this is going to be shift left h units. Whatever h is, that's how many units we're going to shift. And that may seem counterintuitive because that's a positive h. But remember, when we try to find the vertex of our absolute value function, we set the inside of the absolute value equal to 0 to figure out what that x value should be. And that x value ends up, for this one, would end up being a -2. And so that's where that negative shift comes from. And our vertex is -2, 0. So shift left h units. Again, the h ones are a little counterintuitive. They're opposite. So think opposite h. If I have f of x minus h, so something is subtracted inside the operator, so inside of this operation absolute value here, when I had a -2, It was a right shift. So this will be shift right h units. Okay, then we had something that was being added outside of the absolute value bar, so outside of our operation or that applies to our function. So if we have something like this, f of x less k, k represents our vertical shift. And so if it's positive, this one is more intuitive. It's going to be a vertical shift up. Shift up, whatever k is, k units. And that we saw when we compared this to our parent function, we shifted up 2 when there was a plus 2 outside. If I have f of x minus k, what do you think that transformation is going to be? Shift down. So shift down k units. Whatever k is, that's our shift. Then we had some instances where there was numbers out in front of our absolute value. And so these are going to be dilations. Okay, so these were all translations. So we'll call these translations. And those were going to be dilations, meaning our slope is going to become more narrow or less narrow. And so with the dilations, if I have a in front of my f of x, so a is in front of whatever operation is applied to this parent function. For example, here I have a 2 out in front of my absolute value of x. When a is greater than, or the absolute value of a is greater than 1, this is going to be a vertical stretch. Vertical stretch. So just looking at a, and we're looking at the positive value of a, it's going to be a vertical stretch. If a is less than 1 but greater than 0. So when the absolute value of a is greater than 0 but less than 1, so a fraction. Like this example, 1/2 x. This is going to be vertical compress. And then the last type of transformation that we saw here was when we had a negative out in front of our function. And this is a reflection. So when there's a negative out in front of our function, that is going to be a reflection across the x-axis. So use this transformation guide to help you when we're describing transformations. And that's what we're going to take a look at on the next page. We're going to be given different transformations, different functions, absolute value functions specifically, and we're going to describe the transformations. So let's take a look. Okay, so we're going to take a look here. On the back of this page here, I've already written out our problem, so if you need to pause the video, make sure you do so you can get these written down. All we're going to do is compare each of these functions to the parent function. We're going to describe the transformations that have occurred. I'm going to go ahead and color code these. You can do that if you'd like to. I'm using 4 different colors. These are the colors that I'm going to use. And I'm going to use pink just because on the front side, I wrote down information about my translations in pink and blue. So I'm going to highlight the horizontal shift in pink. And I'm going to do the vertical shift in blue, just to help me see it. I will use green for dilation. So stretch, compress. And I will use orange for reflection. All right, we have f of x is equal to absolute value of x minus 5. Comparing this to our parent function and looking at our transformation guides on the front. Okay, well, we have x minus h here, which is our horizontal shift. Remember, it's opposite h, so if it's negative, that's going to be shift to the right. Shift right 5. So we'll be specific on how many units we're shifting. Okay, taking a look at number 2. So this would be like our vertical shift. Absolute value of x plus k. So our vertical shift is up or down, and that one is intuitive. Whatever the sign is, that's the direction. So positive means up, negative means down. Okay, remember it's opposite for your horizontal shift. This would be shift up 9. Taking a look at number 3, we've got that negative out in front. So what does that mean? Well, that's our reflection. And when that reflection occurs, which axis is the function reflected over? You have to be specific. Reflect across the x-axis. Now, sometimes more than one transformation occurs. Sometimes there's a horizontal shift, a vertical shift, and a stretch, and a reflection. So we've got to find all of them when looking at the next function. So taking a look here, what does this 3 out in front mean? So if we have a number out in front, that's a stretch or a compress. So I'm going to highlight that green. And then looking here, this minus 2. Okay, so that's going to be a vertical shift. And so we just want to describe those. And so we've got a positive 3. So if the absolute value of this a term here is greater than 1, it's going to be a stretch. So vertical stretch, and then we want to say by 3, by a factor of 3. And then here, minus 2, what does this mean? Will that be shift down 2? Taking a look at the next example, 1/4 times the absolute value of x plus 6, and I did forget to put function notation out in front. This should be f of x equals, we're talking about functions here. So this number out in front, again, that's going to be our vertical stretch or compress, depending on if this is greater than 1 or between 0 and 1. And then what does the positive 6 on the inside mean? Well, that's a horizontal shift, and we're looking at the opposite. So even though it's a plus, really that means shift left 6. So we've got shift left 6, and then this will be a compress, vertical compress. So vertical compress by 1/4, shift left 6. And then our last example, there's quite a few things going on here. So you've got that negative. What does that negative mean? So that negative means a reflection. If there's a negative in front of your function, it's going to be reflected over the x-axis. Then we have this positive 7 inside of the absolute value. So that's our horizontal shift. And then we have minus 2 on the outside. So that's going to be our vertical shift. So if we were comparing this to the parent function, it'd be flipped over to the left 7 and then down 2. So negative means reflect across the x-axis. That positive 7, that means shift left. Remember, it's opposite. Left 7. And then that minus 2 outside means shift down 2. Okay, now Ms. Wolfer, why is this so important? This is so important because graphing an absolute value function that is written in something called vertex form is super simple. You don't even need a table. And so that's the next section of our notes is vertex form of an absolute value function. And this is what vertex form looks like. vertex form looks like this. F of x equals a times the absolute value of x minus h plus k. What we must know is that h comma k, so h comma k is the vertex. Specifically, when we're looking at this h, you have to write this down. It's opposite h. Notice that in vertex form, h is negative, but when we write it in our vertex, it's positive. And so that's where that horizontal shift comes into play. So opposite h, comma, k. The k will stay as it is. If it's positive, it's positive. If it's a minus, it's negative. So h, comma, k is the vertex. Now there's another key part to vertex form. This a value right here is super important. Remember how we said that that was going to be a stretch or compress and it changes the slope? So a is the slope on the right of your vertex. The slope to the right of your vertex. And then because absolute value is the same distance from 0, your slope is mirrored on the left. Slope on the right of the vertex. And negative a is the slope on the left. Here's where graphing absolute value functions are going to be just as simple as graphing linear functions. Let's take a look at an example of graphing an absolute value function in vertex form. So I'm going to go ahead and put my coordinate plane on here. Let's do this example. F of x equals 3 times the absolute value of x plus 5. Okay, remember, opposite h, comma, k, that is the vertex. So the first step, we want to graph the vertex. Step 1, plot the vertex. The vertex here is opposite h, negative 5, comma, k. There is no k value, so this could be the same as plus 0. And so anytime a k value is missing or an h value is missing, it's a 0. So if there wasn't anything inside here, we would say it's 0. So plot the vertex, negative 5, comma, 0. So let's do that. Negative 5, 1, 2, 3, 4, 5, comma, 0, right there. Second, use the slope to graph the line on the right. So my slope here is 3. Really, that's an a value, but that's okay. So I'm going to go up 3 to the right 1. Up 3 to the right 1. Then, step 3, mirror the slope on the left. So instead of going up 3 right 1 from the vertex, so on the right of the vertex, gotta be specific, this is on the left of the vertex. Okay, so on the left of the vertex, up 3 left 1. And notice that that V shape is forming. We have to form that V shape. If it's not a V, it's not going to be correct. We just connect the dots. Boom, boom. Boom, boom. And we can always check our work. We can plug it into a calculator and graph it and see. Again, find the vertex, opposite h, comma, k. Then plot the vertex and use your slope to the right, opposite slope to the left. Let's do another example. So more vertex form. Let's say we have something like this. F of x equals the absolute value of x minus 2, and then outside is minus 4. Step 1, plot the vertex. So what is the vertex? So the vertex is opposite h, comma, k. So opposite h, comma, k. So our vertex is going to be +2, -4. Remember, our k value stays the same as it is out here on our function, and then we put the opposite h value there. We're going to plot that. So 2, -4, over 2, down 4. Now looking at our slope. Okay, well there is not a number in front of our absolute value. And so the slope on the right for this one is going to be just a +1. There's not a number in front. We could put a 1 and it would mean the same thing. So on the right, we're going to go up 1 over 1, up 1 over 1, until we run out of space on the coordinate plane. And then mirror it to the left. Again, we're trying to make that V shape. If it's not ending up like a V, we did something wrong. Connect the dots. Boom, boom. And boom, boom. Don't forget, you have to make those sound effects. Okay, one more example. Okay, we're going to do one more example, and this time it's going to be an inequality. Same steps. The only difference is we've got our dashed line, our solid line, and our shading. Okay, so taking a look, f of x is greater than -3/4 x, and then outside is +7. All right, so right here, there's no h value. No h value, so h is going to equal 0. Anytime there's a missing h or k, we just put it 0. So our vertex then is going to be 0, 7. Again, this just means it was shifted up 7 from the parent function. Then we have our slope to the right, which is whatever number is in front of our absolute value, which is -3/4. So we're going to plot that vertex at 0, 7. And then our slope is down 3, right 4. So 1, 2, 3, 1, 2, 3, 4. Down 3, right 4. And then opposite on the left. Remember, we want to make that V shape. So down 3, left 4. Down 3, left 4. Now we have to take a look at our inequality symbol. So our inequality symbol is greater than. So that means this is going to be a dashed line, and we're shading above. So dashed and above. All right, so let's connect our dots with a dashed line. And then shading above just means everything above our V shape. So all of this up here. All right, you guys, that is all. I love graphing in vertex form better because we don't have to deal with the tables. So we have our lesson. So we have our practice in class tomorrow. Is only one day for practice, but these are really quick, and so there's no problem getting this done. Make sure you bring questions with me tomorrow if there's anything you did not understand.